Hello everyone, thanks for being here today. I want to talk to you about something that sounds like it belongs in a horror movie but is actually real science. We're going to discuss what happens when stars die in the most violent way possible. We're going to talk about places where the universe itself tears apart. We're going to talk about black holes. Let me start with something simple. I'm holding an apple. Watch what happens when I drop it. Down it goes. Hits the ground. You've seen this a million times. You probably learned in school that gravity is pulling it down. Maybe you picture some invisible force reaching up from the center of the earth and yanking on the apple. That's what most people think gravity is. A pulling force, an attraction between objects. Isaac Newton thought that way too, and he was brilliant. His laws of gravity let us predict eclipses, build skyscrapers, send rockets to the moon. For centuries, everyone was satisfied. Objects attract each other. The bigger they are, the stronger they pull. Simple, clean, done. Then Albert Einstein showed up and said we had it all wrong. He said gravity isn't a force at all. There's no invisible hand pulling the apple. Instead, Einstein said something that sounds completely crazy at first. He said massive objects bend space itself. The apple falls because the Earth has warped the fabric of reality around it. I know that sounds like nonsense. It sounds like the kind of thing someone says when they've had too much coffee. But Einstein backed it up with mathematics, and experiments proved him right. So let me give you a picture that makes this clearer. Imagine you have a trampoline stretched out tight and flat. If you roll a marble across it, the marble travels in a straight line. Easy. Now place a heavy bowling ball in the middle. The trampoline sags, it dips down where the ball sits. Now roll that marble again. What happens? It curves. It bends toward the bowling ball. Not because the ball is pulling on it, but because the surface itself is no longer flat. That's what massive objects do to space. The Earth creates a dip in the fabric of space around it. The apple isn't being pulled. It's rolling down a slope we can't see. Mass curves space, and space tells objects how to move. That's Einstein's big insight. That's general relativity. This works beautifully for planets and stars. But physicists love to push things to extremes. We want to know what happens when you take the idea too far. What if you made something incredibly heavy? What if you took all that mass and squeezed it down into a tiny volume? Let's talk about escape. If I want to leave this building, I just walk out? But leaving Earth is much harder. When I toss this apple up, gravity brings it back down. If I threw it faster, it would go higher before falling. To actually escape Earth's gravity completely, you need to reach a specific speed. We call this escape velocity. For Earth, that speed is about 25,000 miles per hour. That's why space agencies need massive rockets. They're fighting to hit that speed. Go slower and you fall back. Go faster and you break free forever. Here's the interesting part. Escape velocity depends on two things: how massive an object is and how compact it is. If I could magically compress the Earth down to half its current size without changing its mass, the gravity at the surface would become 4 times stronger. You need much more speed to escape. Keep squeezing. Imagine crushing the Earth down to the size of a marble. The gravitational pull at that marble's surface would be insane. The escape velocity would be enormous. And now we arrive at a crucial question. What if you squeezed something so small and kept it so massive that the escape velocity exceeded the speed of light? This is where things get interesting. You see, there's a fundamental speed limit in our universe. Nothing travels faster than light. Light moves at 186,000 miles per second. That's the cosmic speed limit. It's not like a highway speed limit you can break if you're willing to pay the ticket. It's absolute. Nothing goes faster. So, imagine an object so dense that to escape from its surface, you'd need to exceed light speed. But you can't exceed light speed. That means nothing can escape. Not rockets, not radio waves, not even light itself. If you shined a flashlight up from this object's surface, the light would curve back down like a thrown ball. What would this look like from a distance? You wouldn't see it. It would be perfectly black. Void, a hole punched in the visible universe. Things fall in, but nothing comes out. For a long time, scientists thought this was just a mathematical curiosity, a weird corner case that couldn't actually exist. We called them dark stars or frozen stars. It seemed too bizarre to be real. Surely nature wouldn't actually create such monsters. But nature doesn't care what we think is reasonable. In recent decades, with powerful telescopes and sophisticated instruments, we've detected them. They're out there. Dozens of them, maybe millions. We call them black holes now. I want to take you on a journey toward one. I want to show you what happens as you approach these cosmic monsters. This is where physics gets truly strange and where our everyday intuition completely fails us. Picture yourself in a spaceship floating in deep space. Far ahead, you see something unusual. A perfectly circular patch of pure darkness against the stars. As you drift closer, you begin to feel a pull. It's gentle at first, but growing stronger. There's a boundary we need to discuss. A point of no return. We call it the event horizon. Let me use an analogy. Imagine you're paddling a canoe on a river. The river flows toward a massive waterfall. Downstream, far upstream, the current is slow. You can easily paddle faster than the water moves. If you change your mind, you can turn around and paddle back upstream. No problem, but as you drift closer to the waterfall, the river narrows. The current speeds up. Now the water is moving at 5 miles per hour. If you can paddle at 6 miles per hour, you're still okay. You can still escape. You just have to work harder, closer still. The current is rushing now at 10 miles per hour. You're paddling with everything you have just to maintain your position. You're not moving backward, but you're not moving forward either. You're stuck fighting the current. The event horizon is the line where the current exactly matches your maximum paddling speed. In our universe, space itself can flow. Near a black hole, space falls inward, and your maximum paddling speed is the speed of light. At the event horizon, space is falling inward at light speed. If you're exactly on that boundary, you could shine a flashlight away from the black hole and the light would hover there, frozen, unable to move outward because space is rushing inward at exactly light speed. The light stays put, trapped, across that boundary by even 1 inch and you're done. Space is now falling inward faster than light. No matter how powerful your rocket engines are, you're going down. There is no outward direction anymore. The future only points one way, inward. This is deeply strange. Usually we can choose our direction, left, right, up, down, forward, back. But inside the horizon, out stops being a direction you can travel. It becomes as impossible as traveling into yesterday. Time only moves forward. Inside a black hole, the center isn't just a place, it's a moment in your future. You're going to reach it as inevitably as tomorrow will arrive. Now, you might be wondering what happens to someone who falls in. I have bad news. It's not pleasant. The problem is tidal forces. You know how the moon creates tides on Earth? The moon pulls on our oceans, but really it pulls on the entire planet. It just pulls slightly harder on the side facing it. That difference stretches the oceans outward. We get high tides. Near a black hole, tidal forces are extreme. Suppose you're falling in feet first. Your feet are closer to the center than your head. The gravitational pull on your feet is much stronger than the pull on your head. You feel stretched, pulled apart lengthwise like you're on a medieval torture rack simultaneously because everything is being pulled toward a central point. You're squeezed from the sides. You get stretched tall and compressed thin. You become like a piece of spaghetti. The technical term for this, and I'm completely serious, is spaghettification. This happens to everything. Stars get spaghettified. Gas clouds get spaghettified. You would definitely Get spaghettified, but let's imagine you're incredibly tough. Or maybe this is a supermassive black hole where the tidal forces at the horizon are gentler. You survive the crossing, you're alive, you're inside. Looking back, you can still see light from the universe outside. It appears as a bright shrinking circle above you, but you can't send messages out. Nothing you do escapes, you're cut off from the rest of reality completely. We need to pause and think about the tools we use to understand this. When physicists draw diagrams or write equations, what are we actually doing? We're using calculus. Don't let that word scare you. Calculus is just the mathematics of change. If nothing changes, math is simple. A car driving at constant 50 miles per hour forever is easy to describe, but real things don't stay constant. They speed up, they slow down, they curve and twist. Falling into a black hole means everything is changing. Gravity intensifies every fraction of a second. Space curves more sharply. Time behaves strangely. Calculus lets us track these changes. It's like having a microscope for examining motion. We look at what's happening right at this instant. Then we look at the next instant. Then the next. We stitch these tiny snapshots together to create a complete picture of your journey. When we do this, when we follow Einstein's equations of general relativity all the way down into the black hole, they predict something terrifying. A catastrophe, not a crash like a car hitting a wall. A crash of the theory itself. As you fall deeper, the mathematics tells us the density of matter increases, the curvature of space tightens, the numbers grow larger, 1,000, 1,000,000, 1,000,000,000. And then at the very center, the equations produce an answer that makes physicists lose sleep. They give us infinity. The equations say all the mass of the collapsed star is crushed down into a geometric point. Zero size, infinite density, infinite curvature. We call this the singularity. You have to understand something about. Physicists, we're practical people. We measure things 5 kilograms, 10 meters, 12 seconds. We never measure infinity. Infinity isn't a physical measurement. It's a mathematical concept. It's what happens when you divide by zero. If you try to divide by zero on a calculator, you get an error. The machine breaks. The singularity is nature handing us an error message. It means our beautiful theory of gravity has failed. It works perfectly everywhere else. It works near the horizon, but at the center, it gives nonsense. This is the great mystery. We know something is there. The matter didn't vanish into thin air, but we can't describe it. The singularity is hidden behind the event horizon, wrapped in a cloak of mystery. It's a place where space and time, as we understand them, break down completely. So here we are. We started with a simple apple. We dropped it. We asked why. We followed the question into space, into the dark, into a cosmic waterfall. And we've arrived at a point where the mathematics divides by zero and our understanding shatters. It's frightening in a way, but it's also wonderful because it means we haven't figured everything out. The story isn't finished. We have clues. We have equations. We just need to be smart enough to understand what happens when our theories jam up. In the next part, we're going to explore exactly that. We're going to see what happens when the world of gravity collides with the world of atoms. We're going to try to fix the broken calculator. We're going to peer into the heart of the darkness. But for now, just think about that apple. Think about the invisible curves in the space around you. Think about how fragile our understanding really is. Because somewhere out there in the depths, gravity goes infinite, and we still don't know what that means. We've crossed the boundary. We've fallen past the point of no return. We're rushing toward the center. We've talked about the stretching, the tidal destruction, and that's horrible enough. But now we face the real problem, the thing waiting at the bottom, the singularity. And to understand why it drives physicists crazy, we need to talk about measurement. Physics is built on measuring things. The temperature is 72 degrees. The mass is 5 kilograms. We like concrete numbers. But what does general relativity tell us about the black hole's center? It says the density is infinite. The curvature is infinite. Be careful with that word, infinite. It's easy to say, easy to write, but what does it actually mean in the physical world? If I claimed there were infinite books in this room, you know I was lying. The room has walls. The universe has limits. There's no such thing as infinite stuff. When infinity appears in a physics equation, we don't celebrate. We panic. It's an error message. It means our theory has broken down. Think about division. Divide 1,000 by 2. You get 500. Divide by 10, you get 100. Divide by 1, you get 1,000, but divide by 0. You can't. The rules of arithmetic fail. That's the singularity. It's where the rules of space and time divide by 0. According to Einstein, all that material, the dead star, the gas, the unfortunate astronauts, everything gets compressed to a point smaller than an atom, smaller than anything, but it still has all the mass, infinite density. This troubles us deeply because real things don't collapse into mathematical points. Something else must be happening. General relativity is beautiful. It describes the smooth curves of spacetime perfectly. But it's a classical theory. It assumes space is smooth like a rubber sheet. You can zoom in infinitely and it's still smooth. But we have another rule book, a completely separate set of laws for the tiny world, the realm of atoms and electrons. It's called quantum mechanics, and let me tell you, these two rule books hate each other. General relativity says space is smooth and predictable. I can tell you exactly where a planet will be. Quantum mechanics says everything is fuzzy and probabilistic. You can never know a particle's exact position. Usually these two theories stay out of each other's way. Gravity governs the large scale. Galaxies, stars, quantum mechanics governs the small scale. Atoms, photons, they almost never meet. The gravity of an atom is so weak we ignore it. The quantum uncertainty of a planet is so small we can't detect it. So we use one rule book for big things and another for small things. Everyone is happy. But inside a black hole, disaster strikes, we have something that starts enormous, a star, but gets compressed to atomic scales. We need both rule books simultaneously. We're forcing them into the same room, and they start fighting. Consider Heisenberg's uncertainty principle. This is a fundamental rule of quantum mechanics. It says you cannot perfectly pin down a particle. If you try to confine an electron to a tiny space, it starts moving faster. It jiggles and buzzes frantically. The tighter you squeeze it, the more violently it moves. It demands elbow room. Now think about the singularity. Gravity wants to crush everything to zero size, literally no space at all. But quantum mechanics screams in protest, you can't do that. The particles should be buzzing with infinite energy resisting the compression. Gravity says zero volume. Quantum says you need space. Who wins? We don't know. That's the honest answer. We're missing the instruction manual for this specific situation. We need a new theory that unifies them, a theory of quantum gravity. We have candidates, string theory, loop quantum gravity. Lots of smart people working on it, but nobody has solved it yet. However, even without the final answer, we've discovered something remarkable, something that shocked the entire physics community. It turns out black holes might not be perfectly black. Stay with me because this gets weird. It involves the nature of empty space. We used to think empty space was truly empty. Nothing there, but quantum mechanics says that's wrong. Empty space is actually boiling with activity. It's like looking at calm water from a distance. Looks flat, but get close and you see tiny ripples. Everywhere. In empty space, particles constantly pop into existence and disappear again. We call them virtual particles. They appear in pairs. A particle and an antiparticle. They borrow energy from the universe, exist for a split second, collide, annihilate each other, and return the energy. It happens so fast you can't detect it directly. This is happening right now in front of your face. Pop, vanish, pop, vanish. Normally, this doesn't matter. But imagine this happening right at the event horizon. A pair pops into existence. One appears just inside the boundary. One appears just outside. Gravity snatches the inside one and drags it down. Gone, but the outside one hasn't crossed the line yet. It's stranded. Its partner is gone. It can't annihilate. It can't vanish. It becomes real. It flies away from far away. Watching from a spaceship, it looks like the black hole emitted a particle. It looks like the black hole is glowing. This stunned us. We thought black holes only consumed. We didn't think they could emit anything. But the mathematics says they do. They radiate. We call it Hawking radiation, after Stephen Hawking, who calculated this in the 1970s. Here's the catch. Nothing in physics is free to make that. Virtual particle real requires energy. Where does that energy come from? From the black hole itself. The gravitational field pays the bill, and remember Einstein's equation. Energy equals mass times the speed of light squared. If the black hole loses energy, it loses mass. It shrinks. This is extraordinary. Black holes aren't eternal. They evaporate like puddles on a hot day. Very, very slowly. A stellar mass. Black hole would take trillions upon trillions of years to evaporate. But it happens, and as it shrinks, it gets hotter. It radiates faster. It's a runaway process. In its final moments, a black hole becomes tiny and incredibly hot. Then it explodes, a final blast of energy like a million nuclear bombs. So everything that fell in, the apple, the spaceship, the astronaut, eventually comes back out as heat and radiation billions of years later, but this creates a huge problem. We call it the information paradox. In physics, we believe information is preserved. If I burn a book, I can't read it anymore. But in principle, if I collected every ash molecule, every light photon, every smoke particle, I could reverse the physics and reconstruct the book. The information is scrambled but not destroyed, but if a black hole evaporates completely, what happens to everything that fell in? It comes back out as random thermal radiation, random heat. It seems like all the information is genuinely lost. The book is erased. The library is destroyed. If that's true, our fundamental understanding of physics collapses. If information can be destroyed, we can't predict the past from the future. The entire logical structure of science becomes shaky. We can't have that. So there's a battle raging. Some physicists argue the information is truly lost. Others insist it must be hidden in the radiation somehow. Maybe encoded in subtle patterns in the heat. Maybe the black hole's surface stores a record of everything that fell in, like stamps on a passport. We have a name for that idea. The holographic principle. It suggests the entire three-dimensional interior of a black hole might be encoded on its two-dimensional surface, like a hologram where a 3D image is stored on a flat film. Some physicists go further. They suggest maybe the entire universe works this way. Maybe our 3D reality is a projection from a 2D surface. It sounds like science fiction. But we're pushed to these wild ideas because conventional thinking has hit a wall. The singularity and the information paradox force us to be creative, and that's the beauty of it. I started by dropping an apple, a simple everyday thing. But when you ask the right questions about that apple, why does it fall? What if it fell forever? What if it fell somewhere time stops? You end up rewriting the rules of reality. We don't have the complete answer yet. Go to a library, pick up a textbook on general relativity. It will explain the curves beautifully. Pick up a book on quantum mechanics, it will explain the probabilities. But there's no book yet that explains the singularity completely. That book hasn't been written. Maybe someone reading this will write it. We need people who can think about impossible things. People who aren't afraid when the calculator spits out errors because nature is out there. It has logic. It has rules. It doesn't actually divide by zero. We just think it does because we're looking at it wrong. There's a mechanism we haven't discovered yet, a hidden gear in the machinery of reality. When I look at these equations, I don't see a dead end. I see a door slightly open. We can see light underneath it. We just haven't figured out how to push it open yet. Next time you look up at night, don't just see twinkling lights. Think about the holes, the tears in spacetime, the places where the universe hides its deepest secrets. Think about where gravity becomes infinite and time stops. Remember that we haven't figured it all out. The game is still being played. We're just getting started. Thank you.